In this segment, we begin to look at attacks on RSA implementations.
The purpose of this and the next few video tutorials is to show you how some specific implementation attacks can be applied to RSA implementations in practice. The examples that I've chosen are all examples of attacks that will always work on textbook RSA implementations, which you know shouldn't be used in practice, but they will also work on RSA OAP implementations, which is more interesting because, of course, RSA OAP was designed to withstand a large array of attacks. In principle, we will run through RSA, the textbook scheme, to remind ourselves of how it works, and we will have a look at implementation options that are typically chosen in practice to make this rather heavy scheme that RSA really is these days work also on small constrained devices. And then we will run through a number of attacks. We will run through fault attacks, timing attacks, and power/stroke EM attacks. This will not all happen in this tutorial, but over the next few ones. You will see on the slide there's also a little footnote, and this says beware. In order to follow, you really need to have an understanding of RSA, and this is very important. Although I'm now going to run through textbook RSA, I'm going to do so very quickly. So if you're not entirely firm about the working principle of RSA, please go back to the Crypto A lecture notes and revise RSA from there. So RSA is an abbreviation which stands for its three inventors, and it's been around for a very long time. It should be used only with a secure padding scheme, but underneath that padding scheme you will always find the very classical textbook RSA encryption and decryption functions, and we are going to review them now. So RSA is a public key crypto system, which means that every user has got a key pair, a public key and a private or secret key. The typical RSA notation would be to use E for the public key and D for the private key, E for encryption and D for decryption. It all makes quite a lot of sense. And there are three functions that are necessary to specify any encryption scheme. The first function is key generation, then we need a function for encryption and a function for decryption. The principle of public key encryption is to take the recipient's public key and to use this for encryption, and then the recipient can use their corresponding private or secret key for decryption. And you can see this visualized at the bottom of this slide. So let's run through the three fundamental functions in turn. Key generation. We generate two large primes, P and Q, and with that we then compute another large number, and that is n. It can't be a prime number anymore, because it is a multiple of P and Q. We will also compute a number called phi of n, whereby phi is Euler's phi function. And for a number n, which is just a product of two primes, it's defined to be p minus 1 times q minus 1. Then we can actually generate some keys. And typically, we take a convenient value for the public key E, which is often a value that has got a low Hamming weight. That means a low number of ones in its binary representation. And with this number, assuming that it's invertible, mod phi of n, we can then compute its inverse, which we will call D, the private key. And so then there's a public key that consists of the values E and N, and the private key, which often may just be the value D, but sometimes to speed up decryption, we might store not only D, but also P and Q, and sometimes even phi of n. So then let's revisit encryption and decryption. These functions can be written down in a very simple and straightforward manner, mathematically speaking. Namely, in order to encrypt, we take the public key of the recipient, E, and we just take the input message, which has been somehow converted into an integer representation mod n. So we then have this integer representation m, we raise it to the power E, and we do that mod n. And for decryption, we do the similar operation. We take the ciphertext, which again we now assume to be an integer mod n, and we raise it to the power D. and thereby we can recover the message M. So it's very easy to define, very easy to write down. In fact, when you think back to crypto A, it's also very easy to show that this really is then a functionally correct encryption scheme. And if we plug in small numbers, then we can do this with a basic calculator. The challenge, of course, arises in practice that we need to choose P and Q large enough such that a number of factorization attacks won't work. So P and Q in practice, they can't just be simple numbers such as 7 and 11. They have to be very, very large numbers with many hundreds of bits, which means that when we move on to practice, it becomes a real challenge to implement this. So the security of vanilla RSA can be justified by linking it to a number of mathematically known hard problems. And they are hard if the parameters are large enough. But as we will see, and as also already the notion of InCCA reveals, vanilla RSA as such is simply not strong enough. And the reason is that we can very easily manipulate ciphertexts and thereby turn RSA, show that RSA is malleable. And here is the example that again we typically run through in crypto A, which looks as follows. So suppose there has been an instruction to pay £10. So the message, the plain text was 10. So the ciphertext, the corresponding ciphertext would simply be 10 to the power E mod n for whatever E is chosen. An adversary who intercepts the ciphertext can very easily change it by multiplying it with any number raised to the power E. If that then gets transmitted to the receiver, when they decrypt, then 2 to the E to the power D just is 2, which means that the plaintext message that is revealed is no longer 10 but 20. So it looks like an absolutely fine plaintext message, although it has been changed. So this property is called malleability. We discussed this in much more detail in crypto A, and it is the reason why plain vanilla RSA cannot fulfill any strong notion of security. So vanilla RSA, because it's malleable, chosen ciphertext attacks are possible, but even if we wouldn't consider malleability as an issue, it wouldn't fulfill InCPA, of course, either. So clearly something has to be done, and as we discussed before, this would be RSA OAP in most cases when it is used as an encryption function. But let's have a look at issues that arise when you implement RSA. And the issues are, of course, implementation attacks, and they will work on definitely vanilla RSA, but as I said before, many of them will also work for RSA OAP. So let's consider RSA implementations. What ingredients do we need to use in order to make RSA really workable in practice? Because for these huge parameter choices that we have to make, so P and Q will be many hundreds of bits, this clearly is too big to be efficiently computed on a standard processor. Even high-end processors, such as what you would find in your typical laptop, they only operate on 64-bit data words. So this is just a tiny chunk out of a very, very large modulus and or public key. There are a number of key ingredients that people use in practice to make RSA fast. Firstly, they probably choose a special public key. That is either a small number or a number that has got very few ones in its binary representation. Secondly, people choose an exponentiation function or routine that is fast. And then thirdly, they will pay attention to how to do the modular reduction in the exponentiation. We'll run through all of these choices in turn and then visit one more choice. So let's first just look at the sort of decryption where we need to compute C to the power D mod n. So here choosing a small e doesn't really help us. Most likely our D will simply be full size, no matter of the choice of E. A very popular algorithm that can be used to make this exponentiation fast is the left to right binary exponentiation algorithm. And Dan ran through this algorithm with you before. To remind you of the algorithm, I copy-pasted his description on the right-hand side here at the bottom of the slide. And you may remember this. So the description that he has given to you is a very generic one, in the sense that this algorithm can actually be used in both multiplicative and additive groups. And he's written it down in such a way that it fits either group. My description here, that is also on the right hand side but just above Dan's description, is already specialized for RSA. So here it's written down in a multiplicative notation, and it's already written down such that you are recovering a message from a ciphertext. And the process here is very, very simple. So you traverse the secret key from left to right, so from the most significant bit to the least significant bit. We always assume that the most significant bit, so the bit W here, is set to be 1. And then we run through from W minus 1 down to the least significant bit. And then we check. In each for loop, we square the sort of intermediate value m. And whenever we encounter one bit in the exponent, we multiply the ciphertext in. And this will ensure that we are revealing then the message as a result. So it's a very simple algorithm, but very effective. A good speed up for modular exponentiation, which requires very little extra space. Now let's consider the fact that we also need to do a reduction in our squarings and in our multiplies. There are a number of modular reduction techniques out there, and the very popular one is called the Montgomery reduction. Again, Dan talked you through this already, and I've copy-pasted in the Montgomery exponentiation using his notation. So you can see this is again the left-to-right algorithm. You can also see that the first step in the algorithm is to transfer all the input variables into what's called the Montgomery domain. And then we just do the typical square and multiply left to right algorithm. The Montgomery multiplication contains now also the Montgomery reduction, so this is where the reduction actually comes in. And in principle, Montgomery multiplication with the associated reduction is constant time. However, in its original description, it can happen that every now and then, for some specific input values, the result of the Montgomery multiplication and reduction would be larger than the modulus, in which case the modulus has to be subtracted. So this you can see on the slide here at the bottom. Here's an extra reduction every now and then. And you may recall from the last video lecture that I showed you a trace of RSA where you could distinguish squares and multiplies in a power trace, because these are different operations. Here we've got another feature that occurs only every now and then, and you might begin to wonder whether it would be possible to, for instance, notice this specific extra reduction somehow through some sort of side channel. Finally, there is another ingredient that is often used in practice for RSA decryption, and this is the use of the so-called Chinese remainder theorem. You will have encountered this already in Crypto A, although we didn't spend much time on it. It's used actually, or we use it in order to prove that RSA works. And the trick here, or the advantage of using the CRT, is that you can show a specific property, mod P, and then you can show the same property, mod Q, and then the CRT, the Chinese remainder theorem, allows you to argue that the same property must also hold mod N. Now for RSA decryption, what we are aiming to compute is some value raised to the power d mod n. Now we know that n is a multiple, or is a product of P and Q. So the idea when using the CRT is that we take the input value, which on this slide is called x. We first raise it to the power d, but we do everything mod p, and p is much smaller than n, so this will be much faster. Then we do the same, but everything mod q, and then we use the Chinese remainder theorem to compute the result mod n. This gives us a very nice speed up, and it's very, very often used in practice. Now that we have run through various implementation options, let's consider their security implications. We have already considered before, in the last video lecture, that data-dependent features may be visible through some side channel traces. So we've seen this power trace where squares and multiplies would clearly show. Hence you could wonder if the additional subtraction that occurs in Montgomery multiplication may also be visible somehow. So might this be also a side channel? but we also considered last time more active attacks, in the sense that we saw in the video that if you actively get into the chip, you may be able to insert data, or maybe we may be able to get to malfunction a chip in some specific way. And this idea is called fault analysis, and it works beautifully for most cryptographic schemes. There is, in fact, a very straightforward, very generic fault attack that can be applied to virtually any cryptographic scheme. It requires, though, the insertion of faults in very precise locations, and one can wonder if this is possible. Now here, side channels might be useful. You can see on the slide I've pasted in a power trace again from an RSA exponentiation. We can see the different peaks here, which correspond to square and multiply patterns. So if an adversary has got access to such power traces, they may be able to induce faults in very specific locations or very specific timings that correspond to the manipulation of individual key bits. With this in mind, we now consider this generic fault attack. We assume that the algorithm is executed by using the binary left-to-right exponentiation algorithm. We first take some arbitrary reference ciphertext and let the oracle decrypt it, so we receive a message M as a result. This is our reference message. We take the same ciphertext again and again ask the oracle to decrypt it, but this time we fault it in the first round of the for loop. So when the bit after the most significant bit is being used, and we force the bit to be stuck at some value. It doesn't matter which one. For simplicity, we chose here it to be stuck at 0. So when this bit comes, we make it stuck at 0, and then we let the algorithm continue, and we observe the resulting message. Now we check, is this the same as the previous decryption, so as the reference decryption? If so, then the key bit must have been 0 anyway. If not, then we know that this key bit must have been 1, hence we have learned what this key bit was. And so we continue, meaning that we take the same ciphertext again. This time, we fault the decryption in the second round, so at the second bit down from the most significant bit. Again, we make it stuck at 0, and then we observe the resulting message. If it is the same as the reference decryption, then we know the bit must have been 0 anyway, and otherwise we know it's 1, and hence we've learned the next bit. And so we go through the secret exponent bit by bit and recover that exponent. Hence we can recover the entire key with just log of the exponent queries. This brings us to the end of this video tutorial. And to summarize, RSA, although it looks very simple mathematically, is rather complex when you implement it because of the large prime factors that have to be chosen. We need to hence use a few implementation tricks. And every single of these tricks is of course a potential cause for side channels and a potential attack surface for fault attacks.